In this series of videos, we're going to be introducing geological modeling in RMSP. So the items we're going to cover in a series of videos including how to import the module, a basic breakdown of the different data processing modeling tools that it has, a quick little example and a little flowchart sort of illustrating the general idea. And then in subsequent videos, what we'll cover is things like the example dataset that can be used for training, how to process data for use later on in geological modeling, the concept of the geological sequence, which is a pretty important piece, which brings everything together into a single geological model, and the general approach to a concise and powerful workflow, keeping in mind that we are putting together powerful Python RMSP workflows for scalable and really creative geological modeling. The first thing we're going to want to do is import some Python packages. So say our favorites like pandas and matplotlib and possibly numpy. So we can go ahead and import those. And then we'd likely want to import RMSP and the geology. Now we don't actually have to do anything. We could just import RMSP and be done with that. But we probably just want to make our lives a little bit easier moving forward. And we can import the rmsp.geology module and abbreviate it to geo, so we don't have to type out rmsp.geology as geo every time. Before we jump into anything further, it's probably a good idea just to give everybody an overview of what is actually in the box. So within the geological modeling module, we have data types, processing tools, we have submesh and solid functions, we have estimators and estimation methods, and then we also have some modelers, which are really going to be the backbone of everything. So structural plane data, this is sort of strike dip and facing information, facing being sort of the orientational structural plane data, and we'll talk about that data set in a little bit more detail later. We have some pre-processing data tools, such as our clustering tools. I'm not going to talk about those too much, but those are basically for pre-processing. This is even prior to geological modeling, to group data into sensible groupings based on their multivariate relationships, and possibly adding the spatial context to those clusters using our dual space clusterer. But the most important ones we're going to be dealing with are our geo.signed distance. The signed distance is basically distance between different categories for say points or drill holes in space. And then we also have our interval data.get contacts method, which is for extracting contacts from interval data. So this could be like at between different rock types or something to those along those lines. There are various functions in RMSP which support geological modeling. The one under the geological modeler namespace is snap to points, and this is basically a post-processing where you can take meshes and solids and provide a number of points and actually move triangulations to snap to the points. They could be decimated, and there's various parameters which control that. At the heart of our of geological modeling, in the heart of our modelers, we have our RBF Estimator. Now the RBF Estimator works like any other RMSP estimator. It's provide locations and input data, and then it estimates out onto locations. There are various different parameters that control the RBF Estimator. For example, the kernel, or we might choose which solver we want to use, or we might choose to actually use partitions. And partitions are actually a method of dividing our data into partitions based on data density and various parameters. And then those can use to be either improve computational efficiency, or can be used actually to facilitate locally varying anisotropy with our RBF Estimator, basically assigning local anisotropies to each partition. The fast multiple solver is a solver which is supported by our RBF estimator, and this solver is basically facilitates highly efficient, scalable RBF estimation, and can handle millions of points. And then lastly, but importantly, are our modelers. We have various different modelers, and each are for specific types of purposes. We have a surface modeler, which is for modeling volumes. Generally is combined with sign distance data, although it can accept any numerical data such as indicators or grades. And then we have a contact surface modeler, which is basically fitting surfaces to points in space, so things like faults or rock type contacts. We have an offset surface modeler, which is also fitting to points in space, but the shape of the resulting surface will be based on a reference surface that is provided. So if you have things like a topography or another folded lithology, you can use that as a reference, and your resulting surface will follow that. We also have a vein modeler for modeling sort of tabular-like or vein-like features. They're based off of a mid-surface, which is inferred from midpoints of intervals, and then you'll be fitting to hanging wall and footwall. This mid-surface can also be generated from a reference surface, though, in which case, if you have very complex veins like folded veins and things, like, you can provide reference surfaces and the veins will follow those. Then last but not least, the geologic sequence. This is a very important part of it, and this is where all the processing and organization of our geological modeling workflow is going to take place, where we provide modelers and existing solids in different chronologies and sequences, different terminations, to give the best representation of our geological model that we can. So next up, we are going to just walk through the general idea of geological modeling, okay, in RMSP. So basically, we've got a data set or various data sets, however you want to look at it, and we have a number of, say, rock types or features that we want to model. There might be a number of these different rock types we want to model, and they might have different characteristics. So for example, we might have an overburdened surface which requires the use of an offset surface modeler. We have a narrow quartz vein which requires the use of a vein modeler. We have an alteration which is more blobby-like and might require the use of a surface modeler. So the first step would basically be to select the model which is fit for purpose, and then process the data according to what type of model you're trying to create. In the case of a overburden, we'd be extracting contacts between overburden and the other lithologies. In the case of a vein, we'd be using interval data to extract hanging wall and footwalls, although this is done by the class. And then for surface modeler, we would be calculating sign distances and providing that as our data. So then we provide our data, and at that point we also have the option to provide control data. This could be polylines, points, or structural plane data. So this sort of represents the type of thing like polylines digitized from underground mapping, or interpretation, structural measurements. That sort of data can all be used to aid our geological modeling process. And there's various options on how to use that data. Then we would go ahead and set our parameters. Typically, a lot of the parameters you'll be setting would be the radial basis functions, the RBF parameters, setting your kernel, and when I say kernel, I'm referring to the variograms, and which solver you want to use, whether you're going to be using partitions or not. You may also set your snap parameters, and also do things like define whether you want to filter out data after on the other side of a termination, or whether you want to still use that data to guide the surface. And then once we've done that, it's probably a good idea to preview your solids, have a look at them, make sure everything's working out, possibly validate them, and then we can provide them to generate a geologic sequence, And in the geologic sequence, we can set up complex relationships between all our different lithologies to produce our final geological model, and then finally extract the solids, doing things like applying domains and that sort of thing. So I'm going to show a little quick example of how this works. This is not really part of your learning experience, but it gives you a taste so that for future models, future videos, you have some context. So firstly, I will import the some example data. And I'm going to be importing the geo training data set. And so you can find this if you go down here. You will see we've got various data sets here. So we've got this geo training data set that we can import, and we're going to discuss this data set a little bit in later videos. I'm also going to right off the bat just convert this to interval data. It currently comes in as point data, but has everything that you need to convert it to interval data. I'm also going to import the topography from the single vein data set. So example data single vein, got a little spelling error there, which is only human for poor typers like myself. And we can look at the columns quickly just to check what was in this data set. So we can see we've got this rock type column there. So let's go ahead and quickly set up a vein class. Okay, so let's go geo.vein modeler, and we can add interval data, and we can add our data. The variable of interest that we want to look at is our rock type, and then the vein we want to model is 3. Okay, and then what we could do is we could extract the solid from this. So in order to extract a solid, I need to define a grid. My favorite way to do this, or my lazy way to do this, is from spatial extents. So I want it around, and I want the block size to be 10, and then we can view 3D. Okay, so I quickly extracted one at a 10-meter resolution. I can also, if I look at this vein, I can see it's not snapped, so I can quickly snap it just by saying snap equals true. And also another thing I want to show is this outputs as a surface data object. So it shows our hang wall, our footwall, and then these triangulations on the side. We can actually also opt to output the thickness of the vein. And there we're showing the thickness of the vein. Okay, but that was just my little preview, and now I actually want to extract solids from a geological model that have been clipped to topography, and I put all the things we want. So like we could make a geo sequence equals geologic sequence, and then I can, let me just fix that spelling. I can set the topography. Geosec.set topo, and then just give my topo, and then I can dot add model, and then I can give it my vein class, and then I need to give it a name, so I'll call that my vein. And then I will just borrow this line up here. I will go geosec dot to solids this time, because it's going to export more than one solid. And then I'll just go to view 3D, and I'm just going to give this an alpha equals 0.5. It's complaining, but that's okay. It's complaining that the that my topo didn't cover the whole area. That we can deal with other methods, but there I created my little topography, and there's my vein all created, and we're ready to move to the next step of our geological modeling. Okay, so in subsequent videos, we're going to go into a little bit more detail for everything that's required for a geological modeling workflow.